All right, I've started recording. So today we'll be looking at exploring an interview question. And one of the great books is Cracking the Code. Um, so a lot of programmers use this mostly to look at the questions and try to practice it. Um, so all of these questions are like, they separate it into chapters, right, with different strategies. So I guess we can start looking at by uh, sort of one at a time. The more important, I think the more relevant ones can be earlier in the chapter. No, they're all pretty important, but they're different categories. So we could look at some um, objective design questions, I think, because a lot of programming now is objective. Well, actually, recursion and dynamic programming are very, very often asked, and people often suck on that. So we can also take a look at recursion and dynamic programming. Have you looked at recursion before? Okay. Yeah, got it. So let's look at, chapter 8 is recursion. Um, so recursion is basically constructing this tree, but you're doing it in code, so it's not directly being done. Let's just look at and pick a interview question. I haven't looked at these yet ahead of time, but we can take a look at them together. Okay. So we'll go and fire up the IPython interpreter as well, so that we can follow along with our examples. And here, this is just a simple text editor here, and we'll take a look at. Let's look at 8.2. That robot in a grid looks interesting. This is kind of common, I guess, scenario. So let's read the question. Imagine a robot sitting on the upper left corner of grid with R rows and C columns. The robot can move in two directions, right and down, but certain cells are off limits such that the robot can't step on them. Design an algorithm to find a path for the robot from the top left to the bottom right. And so it just says you need to find a path. So let's break this down to what this might look like. You have so essentially, so you have like a grid which looks something like, let's say these are grid cells, right? So we have 3 rows, 1, 2, 3, 4, 5, 6, 3 by 6. So where rows is equal to 3 and columns is equal to 6, right? And it says there are some obstacles. So let's say there are some obstacles X that we can't move through. So just by observation, it looks like there's at least one path from the initial corner, which is let's say S for start and T for or F for finish, right? So S start, T F finish, X obstacle. Valid. What's that? Where's the other path? There's only one possible path, I think. Oh, right here, right? Okay, yeah, but the question asks a path, right? So any path works, right? So in this case, then, we should write something that looks for the path either from here or from here. So it says this is, when you're thinking about this, you can only go right or down choices, right? And so that means if you're here, you only can go here or here, right? So naively thinking at it, if you think in terms of recursion or dynamic programming, is that every step that you do right or down, you're taking away one of the rows or one of the columns, right? So like if I went downwards, I take away all of the possibility of moving rightwards from that row. If I went sideways, if I went right side, then all of this will be off limits to me. So yeah. So let's first yeah. Let's look at how to represent this problem in a data structure first. Right. So this looks like a 2-dimensional list, right? Or it could just be a 1-dimensional list. But if we look at a 2-dimensional array, it makes it a little easier. So what this translates to, if in Python syntax, it would look like here's an S, here's a X, and blah, 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 blah. Like here's one list, and then here's the other list. Of course, with commas in for every character. Right, this is pretty tedious to format it. But here it is. Right, so let's copy this and say this is a row 1. Row 2 is equal to dash. Row 3 is all of that, right? So, I made a mistake. Okay, so row 1. Then we have the map, which is basically grid is R1, R2, and R3, right? So when we look at the grid, okay, so that's the grid. Yes, so it's a nested data structure, right? So it looks like that. Yeah, so we need a function that basically finds the path given a grid and returns the finds any valid path from 0, 0 of the grid to the row column of the end, right? So the sort of attack will do. I mean, there are several ways of solving this, including even looking at it backwards, right? If you look at it backwards, it's like, well, I know I have to get here, tracing myself backwards, then the only way I could have gotten here was whether from the above or the left side, right? And so you would move backwards and do it. So moving forwards is equally valid. So this problem is interesting because it has many approaches, right? So we can take one approach and say, let's just look at it from the perspective of moving from the beginning, because that makes that, that's sort of intuitive. We're only looking at down or right. Like that's what the question is saying, but knowing what this means is like you can also work backwards. So we can maybe do that later. So for so current position, we're in 0, 0. Current row column, okay? So that means we're at 0, 0. And we want to have a recursive function, helper recursive function that moves, that increments this as necessary. So, if the next call we might do like 1, 0, we might do 1, 1, right? And then for some kind of path, path returns a path. A path looks like a string of characters that say either right side or downwards, okay? So for example, it might return a path of like RD, RD, RD. Or in this case, it would be DDD, RR, RR. Right, that is one valid. 2 Ds and 5 Rs. 1, 2, 3, 4. Right. So we have, we can do a while loop. We basically need to keep track of 2 possibilities each time, right? So possible moves, and then we can say while the current So the sort of approach I'm taking here is we'll take this and stick it in the possible moves. So, right? And basically each time we have a split in choices, we'll put it on the possible moves and we'll look at that, right? So basically choice, we put it in possible moves. Okay, so so basically we want to keep trying unless no more possible moves. So I need to check something. I think if A is an array and we say not A, should be true. Not A means it's empty. And if A append, and if we put a 1 in there, then not A should be false, right? So while A they're the same. So while there's still something in that list, right, we'll keep trying, but also we want to stop trying. We basically want to try. So we want to first get of the move. Right? So there's something you can do here, which is if A, you have a function that says like pop, and that returns you 1, right? And now if you look at, if you now look at A is empty. So if we append 1, 2, and 3, we have a list of 1, 2, and 3. Pop takes the first element out, or the last element out. So now A is gone, right? Yeah. So a move, if a move is essentially blocked, right? Then basically here we say if the move is blocked, so what is a move here? This is the current position here is actually going to be 0, 0, right? So we need to look at what the cell is. The cell is going to be from the grid that we passed, and it's going to be a move, the 0th position, and the a move for the 1th position, which basically access this as the index, 0th index and 1 index, right? So does that make sense? So if it basically, let's say position is equal to 1, 2, or 0, 1, 2, then you're really calling position 0 means 1, and position 1 means 2, right? Because it's just accessing those numbers here. There. Ending. How about the start location? End is the grid's length of the grid is the row, and then length of the grid of the first element is the column. Does that make sense? So ending position is 3 and 6. So that means if we do grid and say ending position 0 ending position 1, that should give us... Oh, okay. I made a mistake. So here's a bug. There. Oh, my bad. Syntax error. Right? So now this represents this finishing position. Right? Yeah. So here is a syntax error. There. So cell. So that means if we have a possible move with starting location, starting position. So basically I'm sticking this into the possible moves. Right? And then ending location is here. So if we have a move, we'll look at one of the possible move coordinates. I should, instead of location, I should call it coordinate. Okay, because it's a coordinate. So possible coordinates, basically a coordinate from the possible coordinates, and then I translate that into a cell. And the cell, if it's blocked, then we continue, right? We continue in the loop. If the cell is if the one thing we need to check is if we're at the ending coordinate, right? So if a coordinate is already equal to where we need to go, yeah, then we're done, right? Then we've found the path. So we need to return the path. But now, you know, we haven't quite gotten there yet, but we'll have to construct a path. So one thing, possible coordinates and possible paths to those coordinates. So these are data structures that they need to be exactly the same, right? Does this make sense? Yeah. So it's not so clear. So for example, if I go RDR, right, then the possible path should, so if I went RDR, possible path would be wait, let me think about this. This is not so clean because I want to return a path, right? I want to return a path like this, and I need to have a coordinate. I need to basically track where I am and what the path is. Yeah. Yeah. This. Yeah. Yeah. So here's the coordinate. Okay. And we basically say if we're blocked, we don't want to do anything. But if we're not blocked, I guess we can just do else here, right? Else. I guess we don't even need the else. Not blocked here, which means look at the right and down moves, right? So that means we need to so basically look at the possible coordinates and append the here's the right coordinates and the down coordinates. So the right coordinates is going to be the starting the coordinates. Let me rename these. So naming things is hard. Current, okay? So if we're at the current, it means the right one is, so I'm going to copy paste this. So basically I'm you know what, this is confusing. So let me clean it up a little bit. I think you can do A equals B equals 2. So A is 2, B is equal to 2. Okay. So that means let's just assign them to be the same for now. And then right coordinate except when you go right, if you have a coordinate 1, 2, if you go rightwards this way, your column increases, right? No, it will be 1, 3, right? Because this is the row, this is the column. You're increasing the column. Yeah. In other words, to actually make this clear, because you want code that looks readable, right? So row column is equal to current, and so this deconstructs it. So if A was 1, 2, right, and if you did R C equals A, R is 1 and C is 2. Okay. So let's just construct it here. So this means we need row, but we need column to be +1, right? And this means we need row +1, but column. This is more readable, right? This is the down coordinate. Okay. So then we look at so if A is a list and we want to append it, we can give it some value, right? So then we have this. Let me see if I can append 2 values at once. No, it takes 1 argument. Okay. We'll just do right, and we just do down, right? And so it doesn't matter if it is what we need to check here is if it's an invalid position. Actually, we should do this check before, right? So that means if so we need to check if these are within the bounds of the grid. Yeah, because the ending these new positions cannot be greater than ending coordinates, right? Which is 2 and 5. So if we had something that says new coordinates is equal to like 2 and 6, this is invalid, right? Let me see if it's less than is meaningful here. False. Interesting. False. True. Okay. So that means anything that's valid should be true. But if it's 1, 6, this should be false. Oh, yeah, can't use it. So it's doing it stepwise. It's looking at 1. If it's less, then it's okay. So we need to check ourselves, right? Okay, so what we're going to do is check if these are within bounds. If the column plus 1 is less than the ending coordinates max row, max column, let's put it here, okay? So, yeah. Then we can move right. If row plus 1 is less or equal to max row, then it's valid. Then we say, let's add that here, right? And this ensures that all the things in this list are always valid, right? But when we add or remove from this list, we need to also remember the path. At least in this variation of the solution, we need to keep track of the path. So when we do a pop here, we also have to pop the paths, just so that their lengths are always the same, right? So then possible paths, we also need to append. Basically, it is the current path plus moving right. And then here, we're moving down. Make sense? So so if path was equal to RD, we want to have if we move right, we want to have right. And if we move down, we want to have down. So we're just basically putting that in there, right? In the possible paths. Yes. So if we've found the end coordinates, then we simply need to return the path, right? Because we've already popped it here. Yeah. And similarly, if we popped a path and it was blocked, we can continue. So let's try to run through this in our heads. What could happen is you don't have a possible path, right? So we need to have a catch statement, basically, that says if we've returned from this while loop, meaning all this code didn't return this path, then we don't have a path. Okay? And so the way you would call this is you would say, let's say example grid. Okay? Well, return assigns it, can be assigned, and if you print it, it cannot be assigned, right? If you had a function that says returns string, and you return like here it is, right? If you call it, it returns here it is, right? And then you can assign it, say my variable, and then my var is here it is, right? But if you say print string and say print nope, right? Then when you say it, like when you call it, you only see it on the console, but when you try to assign it my var2, there's nothing, right? Versus my var has a string. Yeah. Yeah, when you're printing it, it is only going to the console to this is the console. So to run this, we just need to call find path and give it a path, a grid, right? So let's try this out. Copying this, pasting all that, and it found it, right? What would be interesting is every time we look at, if we wanted to see this in action, we could say, let's print and say, let's look at tries. This is just for debug, okay? Just for debug. Let me just use this. So every time we, or iterations, right? We print the iterations, we print what the current one is, and we print what the path is, okay? And so this would, if you want to look at how this works, you see? So let's make sure this works. If I set this to an obstacle, then the only path would be here, and maybe any of these. So let's try that. Let's change the grid and then call this. Does that make sense? Right. So then you go here, down, down, right. So it preferred to go down, right? Yeah, but then it realized here, it's clearer if I say failed, right? Like if we hit the X, then we say we hit the X, right? Then we hit the X here. So another case would be if we had no path, right? If this was the grid, then there's no path, right? We're empty. We ran out of possible moves. Yeah, of course there's different, like there's many different ways of solving this, including going back upwards, right? including recursively. This is iteratively, because you see the while loop, but it could also be recursively. So, but let's first understand how this one worked before moving on to the recursive implementation. Uh-huh. So if you look at the printout for this one, right? Or let's look at this this example here. We started looking at it from this 0, 0 position here, right? And so here represents our initial move, right? We haven't found anything, and so what happens is in the code, it'll look and say, well, that means we can have two choices. So long as these are valid moves within the boundary of the grid, I will add them to the possible coordinates and possible paths, right? So once it's added here, then the loop comes back and basically looks at the one. And the one that is popped is the most recent. We know the most recent, if was added, was the downward position. And so hence you see the first one is D. So we moved down, and this code saw that it was an X, it was blocked, and so we continue. We stopped. We just didn't make any new choices here. But if, let's say, if this cell was the end of the grid, then the path that we popped would have been D, right? This side is all of the paths. So, but because it was a dead end, we just kept looking at the next possible path in our coordinate system, which was R. So we used that one instead. And then that one got us a D, and it's because, here. But in the possible paths, there were also other choices, right? Like I guess one thing that could be clear is if I printed the coordinates with it. So let's do it this way, because I think then you'll understand. See, now the first iteration, you have 0, 0 for the move. The second iteration, you moved. You're currently at, I think this is easier to see with a bigger map. This is much bigger, right? So with this map, you're basically starting out from 0, 0, right? And then it's saying I'm going down, Now my position is here. Let's actually look backwards. Let's look backwards. At the 12th iteration, it said, I am currently at position row 4, column 5, and and how I got here, this is how I got here, right? I got here by doing down, down, right, right, down, down, right, right, right. And so that got me 4 and 5. And these were the other positions I could have reached. And these were the instructions to get to these locations, right? In other words, like my most recently added possible move I could have made was going to position row 3, column 3. And to get to row 3, column 3, the path I chose was this one. So 3, 3 is 0, 1, 2, 3, 0, 1, 2, 3. So here's 3, 3, right? So if you look at the way it went down, down, right, right, down, right. That's why the length of these two lists must always be the same, because they represent, one represents the coordinate of where you are, and one represents how you got here. I think there's a online, like, I'll find it next time, but I think we used to use like shared like notepad. Is it free? So you can go to ATT84 and look at yourself. Look at it yourself. Yeah. Yeah, I'll find something like that next time so you can. Yeah. Okay. Let's look at another possible solution. Do we have time? I think I have time. So for one, find path recursive. To do recursively, we need to basically pass the row and column that we're at, and also the path that we took, right? So this one is a little interesting. You'll see recursively is much easier to reason about and much easier to write. So initially, the way you call it is find passive recursive. You pass the grid and you start at 0, 0, and the path you have is nothing, right? And the way you would do it is you can say, basically, you want to look at the current cell and see if it's a terminal position, but making sure that the row and column passed to you were within the grid size. So max row is equal to grid. So let's find the length of the grid, and max column is equal to length of the first row of the grid. And we want to make sure that if the row is within max row, in other words, let's do this. If so and the column is within range, then we have to else we don't have like out of range, right? Probably just return nothing. If we have a valid row and column, then we want to look at the cell, which is the current row and the current column. And if cell is an obstacle, then we also don't want to continue. Otherwise is a path, right? But if it's a path, if we found the terminating ending row, I guess ending row is equal to ending column. If the row is equal to max row and column is equal to max column, then we found the end. We return the path. Otherwise, we look at the cell, and if it's optical, we don't we don't want to continue there. Actually, let's do this way. Assumes the row and column provided initially is valid. So we don't do the valid checking here, because I want to do the valid checking when we are making the move for left or right. Okay. Let me comment all of this out. So if we're at the, we know where we have to be, and so since it's valid, we can look at the cell. If the cell is an obstacle, we don't want to do anything. If the cell otherwise it's not an obstacle, right? But we want to do rightwards. Let's try moving rightwards. Oh no, because I want to make a recursive call like this. Right? And then here is try the downside. So basically, instead of row, we have column, and we check against the max column. But instead of the add 1 to here, and we would have moved right. Okay. Yeah. So where's the case that we return the path? The case that we return the path is if we've row is equal to max row and column is equal to max column. So if we're in this case, we can return the path, right? Otherwise, it's not correct yet because yeah, let me remove this. Hold on. So because usually there's the other way of doing this is you have like D plus the return of the path. Ooh, I might have failed this interview. Okay, so let's try to run through this from zero. Well, I need to capture this, right? Because this is running, but I'm throwing away. Well, maybe not. Maybe not. Maybe not. Let's remove this. I don't want to have too many rows. Yeah, so nothing ran. See, that's the issue I was worried about because path. So one way to debug this is we print out all of the variables we were passing along. Right. So we looked at 1, 0, 1, RD, and RR. Oh, well, because there is no path. It's a dead end. But it still didn't return anything. Because I needed to funnel up this return here. Because the parent that called this needed to return. No. That using a no. Ah, of course. token means it didn't align. Okay. There we go. Okay, that's it. So the reason this worked, well, let's try it for the case that doesn't work. So this should return nothing. This returns nothing, right? Let's not print this. So this returned nothing. Yeah, because there was no path. But if we give it a chance, then it should return me something, right? And the way this works is because when you're calling the recursion here, when this function returns, so at some point, right, at some point you're getting the full path here, right? But the parent that called this function would have called it either on here or on here. So the parent would have gotten the result, and if there was a path, then there is a result, right? Otherwise, if there's nothing there, then it doesn't get a return. So there was nothing returned. That means at some point it will return from right or from down, and so then all of these ifs will continue to execute. So the recursive fashion solution is easier to write if you fully understand how recursion works. Otherwise, this one is easier because recursion, you need to understand like how the call stack works. So it's harder to get going initially, but it's easier to reason about, right? Like you notice like recursive code is much shorter than like, well, they're about the same, but it's still like cleaner to reason about. Yeah, because you don't need to keep track of this yourself, because recursion takes care of the coordinate and path for you, right? Coordinate here and path here. So, yeah, this takes a little more time to understand, but hey, what's the link that I sent you? I just wanted to share this with you. collabedit.com att84. Okay, let me paste this here as well. So I am out of time. I do need to like get going, but hopefully this has been interesting. I felt I almost forgot to do this, and I was like, oh, why doesn't this work? I'm screwed. I failed the interview. So that's one question. Typically, like you should like go through some of these questions, and each question might take you anywhere between 30 minutes to an hour. They should, if you're proficient, they should take you about 30 minutes. So about 10 minutes to think about like how to set it up, about 15 minutes to code it, and 5 minutes to like debug it. Yeah. So anyway, hope you enjoy that. I'm gonna call it we're gonna stop recording now. All right.